Hello friends, welcome to this lecture on computer-aided power system analysis. We have been looking at the process of finding the Y-bus matrix of a three-phase unbalanced system in the presence of a transformer. So, towards that goal we have first derived the Y-bus matrix of a simple 5-bus system which also includes a transformer, but then we have seen that from that it is not very clear that how the matrices corresponding to the transformer can be embedded into the overall Y-bus matrix. So, for that reason we are now in the process of considering the same system, but by removing the transformer from the circuit. So, then therefore, what we have done is that this is the overall Y-bus matrix which we have already derived in the last lecture, which includes also the transformer. So, now we are considering the same system, but this transformer between bus 2 and 3 has now been actually eliminated, and now we have also now denoted all these injected currents, and obviously these voltages are V1 ABC, V2 ABC, V3 ABC, V4 ABC and V5 ABC. So, the voltages are Vi ABC for all I is equal to 1 to 5. So, we will be now writing down the Y-bus matrix of this system following the usual procedure. So, for that we will not write down the equations as we have done, we will now just follow this simple algorithm for forming the Y-bus matrix. So, the Y-bus matrix would be looking like this: I1 ABC, I2 ABC, I3 ABC, I4 ABC, I5 ABC. So, this is how it will look like. So, this is how it will look like. So, and then of course, we have here this, and then of course here this, and then of course here this V1, V5 ABC. So, if we write down these equations, so they will be looking like, so we will simply so Y12, so it will be Y11. So, again as usual we will first draw the grid, and then we do this, and this. So, so then now this one would be Y11 ABC, then minus 1 2 ABC and minus Y15 ABC from this circuit very easily, because this is only connected between bus 2 and bus 3, and this is of course 0 0, these are all 3 cross 3. For I2 minus 1 2 ABC, and this is 1 2 ABC plus Y12 shunt ABC. This is only connected to bus 1, it is not connected to anywhere else directly. So, all of them would be 0. So, all of them would be 0 0 0 0, all of them would be 0. Now, bus 3 is only connected to bus 4, but to any other bus it is not connected. 2 1 and 5 is not connected. So, between bus 3 and bus 4, so it would be 1 and 2, this is 0, bus 5 it is also 0, and at bus 3 it would be Y34 ABC, so it is minus Y34 ABC it is Y34 ABC plus Y34 shunt ABC. Bus 4 would be usual. Bus 4 is Y44 ABC. And this Y11 ABC and Y44 ABC. I mean, this is the same thing which you have already done, and minus Y43 ABC minus Y34 ABC and minus Y45 ABC, because it is connected directly to bus 3 and bus 5. This would be 0, and then last one is bus 5, it is connected to bus 4 and bus 1. So this is Y55 ABC minus Y45 ABC, this is minus 15 ABC, 0 and 0. Again, this is a 15 cross 1, this is a 15 cross 15, this is a 15 cross 1. So this is the Y bus matrix. So we can write down that this is as if the Y bus matrix. So this is, we can say that this is the Y bus, let us say reduced. So this is the reduced, in a sense that note essentially that all these transformer have been eliminated from the circuit, and this is the actual Y bus, and this is the actual Y bus. Now, if we just compare this Y bus matrix and Y bus reduced matrix, I find that this Y bus matrix is actually the Y bus reduced matrix only with the, I mean all the other elements, I mean almost all the elements are identically the same, all elements are identically the same except at bus 2, except at these 4 elements. This is here, this is Y1 is added, here Y2 is added, here Y3 is added, and here Y4 is added. So then therefore, if in this Y bus red, if I add here plus Y1, if I add here Y2, if I add here Y3, and if I add here Y4, if I add these 4 matrices, or rather these 4 sub matrices, I will just simply get this original Y bus matrix. So then our simple algorithm is, so then essentially now basically why it is happening. So let us see that again. So then essentially in general, let us say this is bus P, this is bus S, I mean P stands for primary and S stands for secondary. P primary is secondary. So and if there is a transformer connected here, so this is IP ABC, this is IS ABC, this is VS ABC, and this is VP ABC. So we said that IP ABC, IS ABC is given by Y1, Y2, Y3, Y4, VP ABC, VS ABC, and this positions we can say that this is essentially PP position, that is basically it is connecting the primary current with primary side voltage, primary current with primary side voltage we should complete here. So and this is essentially PS position, because it is connecting primary side current with secondary side voltage. This is essentially SP position, that because it is connecting secondary side with the, I mean it is basically connecting secondary side current with the primary side voltage, and this is SS position, this is because this is connecting secondary side current with the secondary side voltage. Now, here in our case what was P is equal to 2 and S is equal to 3. So, then therefore, the algorithm is very simple, that we will first find out the Y bus matrix of this system by removing all removing the transformer, and then we will simply put these 4 matrices Y1, Y2, Y3 and Y4 at PP, PS, SP and SS location. We will simply add. So, at PP location we will add Y1, at PS location we will add Y2, at SP location we will add Y3 and at SS location we will add Y4 matrix. We will just add these 4 matrices, or rather these 4 sub matrices for the transformers at these 4 locations PP, PS, SP and SS, right. And so, then after we add these 4 sub matrices in to the Y bus reduced matrix, we get the actual system Y bus matrix. Now, here in this case our P is 2, S is 3. So, then therefore, here we can see PP is 2 2, PS is 2 3, SP is 3 2 and SS is 3 3. Say 2 2 would be added at Y1. This is exactly what we have done. At the location 2 3 we would be adding Y2, that is exactly we have done. At the location 3 2 we would be adding Y3 matrix, that is what exactly we have done. At location 3 3 we would be adding Y4 matrix, and that is the and basically that is what we have done. Now, suppose instead of one transformer, now let us say I do have, let us say 2 transformer. Now, let there are two transformers, one is between bus P and S and another is between bus P dash and S dash. So, then therefore, what we will do, we will simply remove these 2 transformers first, and then we will find out the Y bus reduced matrix by the usual process, and then we will add these, and then we will add these 4 sub matrices at the location PP, PS, SP and SS, and basically for this transformer we would be adding this these transformer sub matrices at the location P dash, P dash, P dash, S dash, S dash, P dash and S dash, S dash location. And same procedure would be followed even if there are hundreds of transformers. So, then therefore, given an n bus system, so then therefore, if there are let us say n bus and let us say T transformer, so then what we will do, we will first simply remove these T transformers, form this Y bus matrix reduce, and then corresponding to each transformer we will look at the 2 buses where they are connected, and then we will simply add the 4 transformer sub matrices as those locations as discussed here. So, by this process we now in the stage where we can find out the Y bus matrix of any system in which there are lines and also as well as there are transformers. So, now we have reached a state where we now would be looking into the actual process of fault analysis. Now, to start with the actual process of fault analysis, we will now first find out the Y bus representation of different types of faults, because here in this case we have simply represented the entire system by its equivalent Y bus matrix. So, then therefore, if we wish to include the effect of any particular fault, So, then therefore, we also should have the equivalent y bus matrix, or rather the equivalent bus impedance matrix corresponding to that particular fault, and then therefore, as we will see in the subsequent lectures, by incorporating that fault admittance matrix, we call this fault admittance matrix. By incorporating this fault admittance matrix into the system bus admittance matrix, we would be able to calculate the all the quantities which are of our interest. So, then therefore, so now our attention is to find out the fault admittance matrices of different fault admittance matrices of different types of fault. So, there are faults. So, now what we are trying to do, we are now trying to find out the fault admittance matrix of different types of fault, which would be ultimately embedded into the system bus admittance matrix to calculate the different quantities of our interest. Now, we know that we have different types of fault as let us say LG, that is basically line to ground, and then we have LL, that is essentially line to line, then we have LLG, that is line to ground, then we have LLL, that is line to line, but this ground is not present, and then we have LLLG, that is line to ground. So, we have to find out the fault admittance matrices of different. So, all these different types of fault. So, then therefore, altogether there are 5 types of fault, 5 types. Is of course, for LG there would be AG, BG, CG, and for LL there would be AB, BC, CA. For LLG there would be ABG, BCG and CAG. For LLL of course, there is only one ABC, and for LLLG also ABCG. So, then we may think that there are altogether 1, 2, 3, 4, 5, 6, 7 and 9, 10, 11 types of fault, but then what we will do, for this and this there are only unique type, and from these 3 sets we would be only considering let us say AG, BC and BCG, right. And if we know that how to find out the fault admittance matrix for a particular type of faults in any set, for example, if I know how to find out the fault admittance matrix for let us say fault AG, so then immediately you would be knowing that immediately you would know that how to find out the fault admittance matrix for this fault BG and CG. Similarly, if we know that how to find out the fault admittance matrix corresponding to BC fault, then of course, similarly by following the same procedure we would be able to find out the fault admittance matrix for this fault AB and CA. Similarly, here also we would be looking into the fault admittance matrix corresponding to BCG fault, and by following the same procedure we would be able to find out this fault admittance matrix for ABG and CAG. So, then therefore, here we would be only considering the fault admittance matrix for this 5 types of fault. One is AG, one is BC, one is BCG, then ABC and ABCG. So, we will be looking into this 5 types of faults, and we would be finding out their fault admittance matrix for these 5 types of fault. So, first fault we are talking now the AG fault. So, at AG fault what we have is that we have let us say this is bus A, bus B and let us say point bus C, and then between bus A and G. So, this is ZZ, this is A, B, C. So, then therefore, there is a fault. In fact, we should use fault impedance. So, now for any particular type of fault, when we are talking about the fault admittance matrix, what we are actually trying to say. So, for example, if I say that the current flowing through the fault is, let us say, I A, I B, I C, we should say that I A F, I B F and I C F. So, then IAF, IBF and ICF are the current flowing through the fault. So, these would be connected by a 3 cross 3 matrix such that they can be expressible in terms of VA, VB and VC. So, these voltages are VA. So, these voltages are let us say VA. So, this voltage is VA, this voltage is VB, this voltage is VC and this current is, let us say, IAF. And here of course, because there is no fault is there. So, then therefore, we can say that IBF is equal to 0, ICF is equal to 0 from then. So, then therefore, because it is an AG fault, so then I can say that IBF is equal to 0 and ICF is also equal to 0 and IAF would be is equal to VVVA by ZF. So, it is YF into VA, where YF is equal to 1 by ZF. So, then if that is the case, so then therefore, we can write down the following relation between IAF, let us say IBF, ICF. So, it would be simply YF 0 0 and all the other terms are 0. All the other terms are 0. So, obviously, and indeed that this matrix relation indeed gives these relations. IAF is equal to YF into VA and IBF is equal to 0. This is 0 into this plus 0 into this plus 0 into this and ICF is equal to 0. So, then therefore, this is the fault admittance matrix. Now, let us consider the fault BC. So, now we are considering the fault BC. So, we are now considering a fault BC. So, what I have? So, it is again bus A, bus B and bus C. And for BC fault, what we have is, what we simply have is that we have some fault impedance, we have for some fault impedance ZF, ZF and this. So, it is a BC fault. So, then therefore, there is a fault between bus B and C and the fault impedance is, we assume that this are basically ZF. So, then again as we said that this is VA, this is VB and this is VC and we have IBF, this is ICF. Because phase A is not involved in the fault, so IAF would be obviously 0. Now, we have to find out the expression of IBF and ICF in terms of VB and VC. Now, suppose that this is the point, let us say neutral. So, say this is the point neutral having a voltage Vn. Now, if I apply KCL at this point, so then therefore, IBF plus ICF is equal to 0. So, then therefore, applying KCL at point N, what we have is that IBF plus ICF is equal to 0. What is IBF? IBF is VB minus Vn by ZF plus VB minus VC minus Vn by Zf is equal to 0. So, it is actually nothing but, so we can write down that Yf into Vb minus Vn plus Yf into Vc minus Vn is equal to 0. So, we can write down that Yf into Vb plus Vc is equal to 2Yf into Vn. So, then therefore, Vn is equal to half of Vb plus Vc. So, once we get Vn is equal to half of Vb plus Vc, so then therefore, I can simply find out that Ibf is equal to Yf into Vb minus Vn. So, it is Yf into Vb minus half of Vb plus Vc, or in other words it is Yf by 2 into Vb minus Vc, and Icf is nothing but Yf into Vc minus Vn, that is Yf into Vc minus half of Vb plus Vc, so it is Yf by 2 Vc minus Vb. So then therefore, if I write down these equations in matrix form, what I will get is that I will get Vc, because If is 0, so then it will be 0, 0 and 0, and Ibf is Yf by 2 Vb minus Vc, so we can simply take Yf by 2, and this is 1 minus 1, and this is 0 minus 1, 1, and it is Vc minus Vb, so it is minus 1, 1. So then therefore, this is the fault admittance matrix. So this is the fault admittance matrix. So this green colored, this is the fault admittance matrix. So this is the fault admittance matrix. Alright, so far we would be only denoting this fault admittance matrix as Y fault. So Y fault is essentially this. So this green colored. Okay, now let us look at the another one. Now let us look at BCG. If I look at BCG, so then therefore I have again phase A, phase B, phase C. Now between phase A, phase B, and then so we, as usual, we said that this is phase A, this is phase B, this is phase C. We said that this is point N, fault impedance is ZF, this is ZF, this is ZG, this is the ground impedance. This has got voltage VA, voltage VB, voltage VC, and as usual IBF, ICF, and this current is 0. So again IAF is equal to 0. And if I say that this is Ig, so at point n can say that IBF plus ICF is equal to Ig by applying KCL. And IBF is equal to, so then therefore what is IBF? IBF is, so IBF is equal to YF into VB minus VN and YF into Vc minus Vn, that is equal to Ig. Ig is Yg into Vn, where Yg is 1 by Zc. Please note that Yg, Yf, Zf, Zg, everything are essentially complex quantities, but just for the sake of brevity we are not really putting this overbar. So then therefore we get Yf into Vb plus Vc is equal to Vn Yg plus 2Yf into Vn. So then therefore Vn is equal to Yf by Yg plus 2Yf into Vb plus Vc. So IBF is equal to Yf into Vb minus Vn. So it is Yf into Vb minus Vn is Yf by Yg plus 2Yf into Vb plus Vc. So it would be Yf, it would be Yg plus, so it will be Yg plus Yf by Yg plus 2Yf into Vb minus Yf by Yg plus 2Yf into Vc. Yf by 2Yf by Vc, right. Similarly, ICF is equal to Yf into Vc minus Vn, so it is Yf to Vc minus Yf by Yg plus 2Yf to Vb plus Vc Yf minus Yf by Yg plus 2Yf into Vb plus Yg plus Yf by Yg plus 2Yf into Vc. Now what we will do is we will do a little simplification. Now Yf into Yg plus Yf by Yg plus 2Yf, what we will get? Yg plus 2Yf. So what I will get? 1 by Zf Zf into 1 by Zg plus 1 by ZF by 1 by ZG plus 2 by ZF 2 by ZF. So it is 1 by ZF into ZF plus ZG by ZF plus 2 ZG. So it is ZF plus ZC by ZF square plus 2 ZC ZF. So then therefore let this is A1, let, and also minus and YF into and YF square by YG plus 2YF. So what I will get? I will get is 1 by ZF square into 1 by ZG plus 2 by ZF. So what I will get is ZG ZF into ZF plus 2ZG into ZF square. So this would be equal to Z as well, so it will be ZG by ZF square plus 2ZG ZF. 2ZG ZF. So then therefore it is, let's say B1, say. So then therefore if I utilize this, so then what we will get is IBF is equal to A1 VB. So then therefore you can say that IBF is equal to A1 into VB minus B1 into VC. A1 into VB minus B1 into VC, and ICF is equal to minus B1 into VB. ICF is equal to minus B1 into VB plus A1 into VC. So then therefore utilizing this, and IAF is equal to 0. So these are the three equations. So then therefore IAF, IBF, ICF is equal to IF is equal to 0. So it is VA, VB, VC. IF is equal to 0, so all should be 0. It is 0 A1 minus B1, it is 0 minus B1 A1. So it is A1 minus B1 and minus B1 A1. So that is, so this is it. So then therefore this is nothing but, so this is nothing but Y fault. So this is the Y fault matrix corresponding to the BCG fault. So we are still remaining with two types of fault, ABC and ABCG fault. So we will be deriving their fault admittance matrices in the next lecture. Thank you.